Hi, welcome back to statistics class. Our topic is about the test of association and independence. Specifically, we will talk about chi-square test. Dear students, a certain objectives of the study requires an appropriate statistical test. So if your objectives is not about testing difference among groups, but rather about association, then we have to use a test of association. So today we will talk about the Pearson chi-square test of association. I will introduce it to you, and then we will discuss the chi-square test formula, and let's have an hypothesis testing example and then exercise. Okay, so today we will talk about the chi-square test for independence. So the chi-square test for independence is also called Pearson's chi-square test or the chi-square test of association. And it is used to discover if there is a relationship between two categorical variables. When I say categorical variables from the word itself, category, so it's like, for example, your level, your gender, your degree, your program. So that is categorical variables. If you want to discover the relationship between two categorical variables. And then this chi-square test is also used to compare the difference of the sample frequencies with the expected frequencies. And it is a statistical test which comprises three applications, namely, we can use chi-square test as a test of goodness of fit, test of association or independence, and test of homogeneity. Also, chi-square test is a test for independence and is used to determine whether two variables are related or not. However, we will just focus our attention to the application of chi-square test to test for independence between variables. To test for independence is used to determine whether two variables are related or not. So as I've said, we'll just focus on test of independence using this chi-square test for independence or Pearson chi-square test or test of association. So now we have some example. It is actually found in your textbook. So a development officer for athletics is interested in whether gender is related to preference for certain sports. Or shall we say, if I am a girl or if I am a woman, do I prefer some certain sports or not? So the officer is interested only in an individual's preference for baseball or football. So on the option of the study is only baseball or football. And then we have here the observed frequencies are presented below using a contingency table. So we can call it as contingency table where it contains the observed values in each category. Let's say, for example, for male. And then for baseball preference, so there are 17 of them who preferred it. So we can call it as observed values for male who prefers baseball. And now, here, we have here the contingency table or observe values for sport preference by gender. So a contingency table containing R rows and C columns. So this is the R rows and this is the columns. So you can refer to this as R by C table. In some textbook, you could also see this R by C table. So the row and column totals are called marginal frequencies. So this is the marginal frequencies. Sometimes marginal frequencies are called row marginal total and column marginal total whose sum is the grand total. So in this contingency table, one variable is assigned to the rows and the other to the columns. So we can call here the 57, this is the row marginal total. So in the row of male, you have the row marginal total, 57, and then the row marginal total for female, we have 52. And also this is the column marginal total, we have the 50 and then the 59. So we call this 57, 52, 50, and 59 as marginal frequencies. And then this 109 is the grand total. So this is the row marginal frequencies, and this is the column marginal frequencies. So let's talk about the formula, or let's discuss the formula. Pearson chi-square test is sometimes called chi-square test of association and is one of the most used statistical methods to test whether there is an association between the row variable and the column variable. So here's how should we read the formula. This is chi-square. Chi-square is equal to summation of OI minus EI quantity squared over EI. So this is our formula 3.1. And our degrees of freedom is the row, this is number of rows, minus 1 multiplied to the number of columns minus 1. So that's how we get a compute for the degrees of freedom, or DF. We will use this for our tabulated value later on. So when you see this formula OIJ or OI, this is the observed frequency falling in the ith row and then the jth column. Say for example, as we have mentioned earlier in the contingency table with the ith gender and then the sport preference. So EIJ or EI is the expected frequency falling in the ith row, jth column. So when we compute, this is expected frequencies. This is expected frequencies. Ij is row total multiplied to the column total divided by grand total. So where R is the total number of rows, C is the total number of columns, and DF, as I've said, it is degrees of freedom. Okay, so statistical hypothesis for the test of association can be stated in either of the three. So we can have this in textual presentation, HO, or our null hypothesis. There is no association between the gender, or this is our row variable, and the sport preference. And then our alternative hypothesis is there is. Always remember, it signifies significance. So there is association between the gender and the sport preference. And then we can also use in our null hypothesis, there is no relationship between the gender and the sport preference. And then there is relationship between the gender and the sport preference. Or we can use the row variables, you can change it to gender, is independent of the column variable or sport preference. You can change it or specifically specify it. So our alternative hypothesis can be the row variables is dependent of column variables. So let's have some review of for decision rule. So this is the Pearson chi-square decision rule. It is actually default. In the chi-square test of association, we reject our null hypothesis and accept the alternative hypothesis if the computed value of our chi-square, it is based on the data, is greater than or equal to the tabulated value of the chi-square for a degrees of freedom and at specified significance level of alpha. Or statistically, we can present it this way. Our chi-square, this is our computed chi-square value, is greater than chi-square tabulated. So meaning tabulated, it is based on a table, a distribution, which you can find in your textbook, or this is a chi-square table. So if your computed value is greater than the tabulated value, then reject HO. Okay, so let's have some remarks. The test is valid if at least 80% of the cells have expected frequencies of at least 5 and no cell has an expected frequency less than or equal to 1. And then if many expected frequencies are very small, researchers commonly combine categories of variables to obtain a table having larger cell frequencies. And generally, one should not pull categories unless there is a natural way to combine them. So let's have some example for you to better understand it. Again, this is called as contingency table. So let us now solve the problem beforehand to test whether gender is related to preference for certain sports. So first, our step one, state the null and alternative hypothesis. So our null hypothesis, the sport preference is independent of gender. And then our alternative is the sport preference is dependent of gender. And then our level of significance, 0.05 by default or usually used. And then our test statistics, we just have to present the necessary data. So this is our contingency table, the observed values. So we already have the observed values or the frequencies. Then we have to compute for the expected. So reminder, this 17 value is the observed value in O11, meaning the first row and then the first column. So intersection, this is O11. Okay. And then 19 is the O22 because in the second row and then the second column. So that is observed value in 22. And then 40 is the observed value for the first row and on the second column. So now, we have to recall our formula that chi-square is equal to the summation of observed value of I minus E expected frequency quantity squared over EI. So we have to compute for these expected frequencies. Since the observed frequencies is already given, we have to compute for the expected frequencies to complete this formula. So when you get the observed or the expected frequencies, this is computed by multiplying the row total. This is actually the marginal frequencies multiplied to the column total divided by the grand total. So E11, so in each observed frequency, ith column, ith row, jth column, we also have a corresponding expected frequencies using the marginal frequencies. So 57 times 50. So this is the marginal, the row marginal tot frequencies. This is 57 multiplied to 50. So, okay, that is divided by 109, that is 26.14. So, this is our expected frequency in the first row and then the first column. And then for expected frequency for the second row, first column, that is 52. 52, this is the second column. 52 multiplied to 50 because it is first column. Multiplied to the grand total is equal to 23.85. And then for E12, or the expected frequency in the first row, and on the second column. So it is here. So we have to compute for the marginal frequency 57 here because the first column, first row, and then the second column. This is here, found here, 57 multiplied by 50 because in the second column, divided by 109 or the grand total. And then the E22, the expected frequency in second row and then the second column. So this is here, 52 second row, second column. So 52 multiplied to 59 divided by 109, that is 28.14. Okay. And then for step 3, this is now our corresponding contingency table with observed and expected frequencies. At first, we only have the observed values. Now we have computed for the expected frequencies, so we have to put it here. So for E11, the first row and the first column, we have computed 26.14. And then the E21, we have 23.85. And then for E12, we have 30.85. And then for E22, we have 28.14. Again, that is E11 and then E12. So now we will complete our calculation. Here, chi-square, this is a computed chi-square, is equal to summation of observed values minus expected frequency rather, divided by expected frequencies. So correspondingly, we have here 17, this is observed values, minus the expected frequency, we have 26.15, then square it, divided by the expected frequency. This is 26.14 or 15 if we have to approximate it or round off. So 26.15 and then another 33 here. This is 021. Then we have the 23.85, our expected frequencies, and then divide by the expected frequency, 23.85, until we have here the 19 minus here, the observe 022, and then E22, we have 19 minus 28.15 divided by 28.15. So by summing all the values, our computed value for our chi-square test or the computed chi-square is equal to 12.40. Again, applying the steps of hypothesis, we have our stating our critical region or our decision rule. So this is our decision rule. Reject HO if chi-square or computed chi-square is greater than chi-square alpha DF, or we call it as chi-square tabular or tabulated value, where x or chi-square is equal to 12.40 and our our tabular chi-square value with a corresponding level of significance here 0.025, and then our degrees of freedom is equal to 3.841. So since 12.40 is greater than 3.84, hence we reject HO based on our decision rule. So how do we get this value, the 3.84? So observe that when you compute the degrees of freedom, we have to compute it as it is needed as we look into the tabular value. So R, number of rows, minus 1 multiplied to the number of columns minus 1. So we have the two columns for rows, two gender minus 1, that is 1, multiplied to two sports, baseball and football. 2 minus 1 is equals 1. So 1 times 1 is equals to 1. So when we get our chi-square distribution or critical values, we have here degrees of freedom, here 1, DF, and then the level of significance, 0.05 at 5%. So our value is 3.84. So now stating or applying the steps of hypothesis testing, this is our critical region. And then our state your decision based on our critical region, we reject HO. So by conclusion, the sport preference and gender are dependent. So you have to base it on your hypothesis. So they are dependent. This means that sport preference is statistically related to gender. In some studies, research has clearly demonstrated that sports are gendered activities as well as social contexts in which boys or men are more actively and enthusiastically encouraged to participate compared with girls and women. So, however, some sports are likely encouraged for girls or women as well. So, for you to practice, if you know how to calculate this chi-square test, consider this data. So if you have computed the chi-square, which is approximately 65.46, and you have rejected the HO, then congratulations. So have your practice exercise for this. So this example two is the distribution of 450 students is classified according to year and smoking in public places. So the question is there an association between year and preference about smoking in public places? So use 0.05 level of significance for your practice exercise. So, for a reminder for us, we have learned about the test of association. So, consider this text from Ellen White, Counsels for the Church. Young persons who are thrown into one another's society may make their association a blessing or a curse. Even in statistics, we have this test of association. So, right now, you have to know, you have to test whether your association with other people, with your friends, is a blessing or a curse, or your association with them is a blessing or a curse for them. So may God bless you, dear students. And for our next topic, we have the Sperman Rho correlation. Thank you and see you.